In the next few videos, we will consider the amplifier bias current and how to generate it. The amplifier bias current is what makes it possible to easily implement voltage control of quite a variety of parameters in various circuits. Again, remember that our coverage focuses on the LM13700, but the general ideas should transfer over to most OTAs. For the 13700, the absolute maximum current into the amplifier bias current input is 2 milliamps, so in general you want to stay well below that. Typically the recommendation would be to stay below 1 milliamp. As mentioned earlier, the amplifier bias current is what controls the gain of the OTA. And there are two cases. There's the case where you are not using the linearizing diodes and the case where you are. When you're not using linearization, the output current is given by 19.2 times IABC, the amplifier bias current, times the input voltage. Now do note that that input voltage is the differential input voltage at the two input terminals of the OTA, not the input voltage from whatever your source is. That is usually dropped down to a much lower level. Also, in most cases, one of the two inputs will be grounded so that we have a single input, and we're just going to call that Vn for the moment. It is important to note at this point that this is dependent on temperature. The 19.2 term is actually 1/2 of the reciprocal of the thermal voltage. In other words, 1 over 2 V sub T, which is equal to Q, the charge on an electron, divided by 2 kT. Now the K is Boltzmann's constant. The T is temperature. So as T increases, the 19.2 decreases. We may derive this in a later video. Depends on whether I get around to it or not. In the case where you are using the linearizing diodes, the 19.2 I sub ABC Vn is no longer valid, and the formula that is used is the output current is equal to 2 times I sub S, which is the input current. That's a little bit problematic. We'll talk about that in a moment. Times IABC divided by I sub D, the diode bias current. Now note that for good linearization, you want to make I sub D reasonably large, say about 1 milliamp, but the larger you make that, the smaller your output current goes, so you've got a trade-off there. Do note that I sub S, the actual input current, must be less than 1/2 the diode bias current. Now here's another part of the puzzle. Since I sub S needs to remain less than 1/2 of the diode bias current, then you want to make the diode bias current as large as possible so that you can make your input current as large as possible to maximize your signal to noise ratio. Assuming that we have set the diode bias to about 1 milliamp, then that means we need to make sure that our input current remains below about 500 microamperes. Now, determining the input current can be a little bit tricky because of the nature of that input. However, we can make some assumptions and we can come fairly close by simply finding the Thevenin equivalent of whatever is connected to that input. And if we assume that we are using a single-ended input with the other input grounded, then that input to which we're connecting our signal will be very close to ground. So if you get the Thevenin equivalent, you've got a voltage source and a resistor to ground effectively, and so you can calculate the current. Now that will be approximate. It certainly will not be exact, but it will get you in the right ballpark at least. Now, another thing to note about our little output current formula here is the 19.2 is not in there. Now remember, the 19.2 was the term that made the output current dependent on temperature. It's no longer there. So here is another advantage of using linearization. Not only can we increase the input signal to maximize our signal to noise ratio, this also effectively gets rid of a very large percentage of our temperature dependence. One note here, when you are using linearization, the output current is typically less than it would be without using linearization. Now you take care of that in your output stage, as we will see later, so it's not really a problem, but that is generally true. So, how do we go about generating the amplifier bias current? First, if you look at the schematic of the LM13700, you will see that there are effectively two PN junctions from the amplifier bias input to the negative supply, meaning that the amplifier bias input is about 2 diode drops above your negative supply. If you're running plus and minus 15 volt supplies, then that amplifier bias input is probably going to be between minus 13.5 and minus 14 volts, somewhere in that region. It will vary a little bit depending on the amount of current into that input. This structure, these two PN junctions from the amplifier bias input to the negative supply, is exactly why you need to be very careful with that input. And very specifically, this is why you do not want to connect that directly to ground. If you connect the amplifier bias input directly to ground, then you've got 15 volts across two forward biased PN junctions. You're going to let the smoke out of those puppies. They are not going to survive that. You will destroy the device, then you throw it away. So be really, really careful. In general, standard practice is to do something to make sure that you limit the current into that input. We'll talk more about that at length in other videos. Another note is when you are prototyping, you need to be very careful when you're moving things around. Always, always, always turn the power off before you go changing things. That's a good idea anyway, but particularly with this device where you might inadvertently touch ground to that pin with the power on, you just destroyed the thing. So be extra careful with these. In just routine run-of-the-mill situations, all you might need to do is connect a resistor from some sort of control voltage input to the amplifier bias current. You'll need to pick that resistor to make sure that the current cannot exceed 2 milliamps, and in general you want to select it so it will stay well under 2 milliamps. So if you had, for example, a plus and minus 5 volt control signal, then you would have as a maximum voltage 5 volts minus about minus 14 volts, so that's about 19 volts. If you put in a 20k resistor, that would limit the current to just under 1 milliamp. Now you could make it smaller than that if you desired, and that would be okay. If you wanted to consider the absolute worst case possibility, if you're running plus and minus 15 volts in your circuit, probably you would expect no voltage anywhere to be greater than 15 volts, so that would give you almost 30 volts maximum between the 15 volt supply and the amplifier bias pin. So a 15K with just under 30 volts total would be just under 2 milliamps. So a 15K would suitably limit the current into that to under 2 milliamps. Note that you can make this a manually adjustable amplifier by connecting a potentiometer between two different voltages, perhaps your plus and minus 15 volt supplies, and then connect the wiper to the resistor that goes to the amplifier bias input. This will give you a variable gain amplifier. Now, That's usually overkill because it's just as easy and cheaper to do this with an operational amplifier. But if you happen to have a spare OTA out of the dual package and you needed a manually adjustable gain, then you could actually use it to do that. Now, that's absolutely the simplest case of driving the amplifier bias current. This has quite a number of problems. It has limitations. It's not particularly accurate. And so in our next video or two, we will look at more complicated ways of creating that amplifier bias current. Control signal, control signal, control signal, control signal, control signal,